Hello everybody, Ghazal is here and I'm going to talk about one of the projects that I did during my PhD where I use machine learning in my own research. So what we are doing in paperclip LiDAR team in physics department is we're sending a very strong laser up to the atmosphere, as you can see the picture here. And then this laser interacts with the molecules in the atmosphere and scatter back. And then we are collecting these photons, and we using these photons we can tell what's happening in the atmosphere, like we can tell you what's the temperature profile and many more things. Like we can, depending on the laser type, we can give you more information about the density of different molecules in the atmosphere. One typical scan when we record our signal looks like this guy in plot B here. So what we see is photon counts in x-axis and altitude in y-axis. For example, we can say that about 50 kilometers, we received about 1,000 photons per the specific time integration time for that specific height. That being said, we have these scans for each minute, and our device is operational overnight. So it means that we have lots of scans per night, and we are operational in most nights of summer and spring, and many nights of fall and winter. We have this device working from mid-90s. It means that we have a big set of data. When we are looking at each scan individually, we realize that not all of them look like this guy here, and many of them have really weird shapes, and we call them bad scans. Before doing any processing of data, we really need to get rid of these bad scans, because they are going to make biases for our model at the end of the day. So we really need to take care of them. And sometimes we see many of these bad scans that can happen because we have some light pollution, or the level of laser drops a lot. We also can have scans with traces of aerosols and clouds. They are not necessarily bad. Actually, they are good scans, but they show the atmosphere in a non-clear condition and in the conditions of having, for example, clouds in the atmosphere. One thing we need to do is like making classifications of these scans, and knowing if they are good scans for clean or good scans for cloudy or aerosol things. We will have different ways of retrieving data from atmosphere. One way to get rid of bad scans is to find a logic. For example, we can say that at 80 kilometers, if we see less than 100 counts, we have to discard that scan. But this is not really helpful, because we might see really different shapes like this guy, or we might have unpredicted things like this guy when we see the whole scan moves forward because we had a high background there. So none of these logic-based methods will give us a very good answer, and we will give us a very good classification. Here is the place that I thought that maybe machine learning can help us a lot. What we did was we labeled 3,000 scans, and then we used a supervised learning algorithm, and we trained our model. Later on, we used our model to do predictions for unseen data, and the result was actually really nice. As you can see, for example, in this plot and this plot, we see that we had 209 scans predicted as good, and they were really good, 56 as bad, and they were very bad. Whereas the ones that they were predicted wrongly are really a small number of cases. These guys are called confusion matrices, which we are going to talk about them in this course in details. Having this in mind, we thought that this is really good, but we don't really want to have labels all the time. What about we use unsupervised learning? In unsupervised learning, we know that we do not need to have labels, and this is like data-driven methodology. So for each night of measurements, when we had less scans, we decided to cluster them. And actually the result was quite interesting. As you can see here, we found three quite distinct clusters from each other. And then we went and looked at our scans to see what they mean. You see that here the blue scans giving us the scans that we know they are good scans. They are having a really good number of counts. They are really strong and they are good. However, the red and green one here are the scans that we know they are bad scans. And here you see the average of all the scans here, which makes this guy here, and this guy here. Moreover, we could find these outliers as well, and these outliers are the outliers we know that they have high background counts. So using unsupervised learning, we could somehow make our our data being clustered, and when we look at clusters, we could realize that this cluster is the cluster we will classify as good or label as good, and the other ones are bad scans. This was quite interesting for us and gave us the idea that maybe we can use unsupervised learning to find anomaly and to do anomaly detection. We are interested in a stratosphere and to find smoke in a stratosphere because they are quite rare events. And at the same time, physically, they are quite interesting, and they have some impacts in the whole climate for us. One thing that we might see aerosols or smokes in higher altitudes in a stratosphere, which is about 12 to 15, like the stratosphere starts about 11, 12 kilometers in London, is happening when we had wildfires. So, for example, during the wildfires of Saskatchewan during late June and early July of 2002, we realized that we detected these fires. So we were thinking that in the case of, if we look at all scans in months of July, and if there is no smoke, we expect to see maybe a very big one cluster and maybe some outliers here and there, but major scans will be all making a big, huge cluster because they are all really looking similar. For months of, it was the case for many months actually, but for the month of July 2002, we saw that we have 4 different distinct clusters. And then when we looked at each cluster, we realized that actually cluster 1, you can see here, it shows very clean atmosphere. These plots are the plots of extinction coefficient, which is a way for us to realize how much of the radiation was absorbed by the atmosphere. When we have high loads of aerosols, we expect that this value goes higher. Here you see that the whole thing looks clear, whereas in plot B, we have small loads of aerosols at this altitude, and you see the numbers are smaller, is about 0.2, 0.3 mostly. However, for these other 2 plots, C and D, you see that now the numbers are getting larger, and they are mostly they mostly look like that we have a high load of aerosol in these 2 plots, but in 2 different altitudes. So using unsupervised learning, we were able to make an anomaly detection algorithm to find trace of smoke in a stratosphere. If I want to give you a summary, I will say that we successfully implemented supervised and unsupervised methods to classify raw LiDAR measurements. And we realized that ML is quite a robust method and it gives us really high accuracy. When we use supervised learning, our accuracy was about 95%. And we also showed that unsupervised schema can be potentially a very good method to use for anomaly detection. That's it.